In 2009, 3 scientists published the exact formula for a dust bowl. Not a theory, not a hypothesis. A peer-reviewed, model-validated, causation-confirmed recipe. Specific ocean temperatures, specific land conditions, specific feedback loops, that when combined, produce the thing that killed 7,000 Americans, destroyed 100 million acres of farmland, and turned the sky black at noon in the 1930s. Now, in April 2026, every variable in that formula has reassembled across the southern plains. The drought is in its 6th year. The ocean temperatures match. The soil protection infrastructure has been quietly dismantled. So why is the federal government completely silent about it? Stick with me, because the answer is more disturbing than the storms. If this already has you thinking, hit like and subscribe to the Skylab, because this story is still running, and we'll be here breaking down every single part of it as it develops. New storms, new data, new drought readings. You're going to want to be here for what comes next. Now, let us get into it. Part 1. The claim no agency will make. On March 15th, 2026, the sky above Lubbock, Texas turned the colour of a dying star. Not metaphorically, not poetically, literally. A wall of particulate matter so dense that the instruments designed to measure air quality simply gave up trying to make sense of what they were reading. The EPA's air quality index tops out functionally at 500. That number represents conditions so dangerous that every health agency in the country classifies them as hazardous. Stay indoors, seal your windows, do not breathe outside air. Lubbock recorded 1,400. The instruments weren't broken. The conditions were just operating in a range the scale was never designed to describe, because the people who designed it didn't think they'd need to. Think about that for a moment. We built a measurement system, and reality exceeded it. That's not a data point, that's a warning. The same week, the National Weather Service office in Amarillo issued what it called a haboob warning. If you're not immediately familiar with that word, you're not supposed to be. A haboob is a type of dust storm specific to desert environments. The Sahara, the Arabian Peninsula, the arid interior of Australia. It's a term forecasters use when a collapsing thunderstorm outflow drives a wall of desert dust across a bone-dry surface at speeds high enough to move cars off roads. It is not a word that was ever supposed to appear in a Texas Panhandle forecast, and yet there it was, in official government language, issued by federal meteorologists who apparently decided that the standard vocabulary of American weather no longer captured what they were looking at. That same storm, or one of the storms from that same period, because they were coming in sequence by this point, caused a multi-vehicle crash on a major highway, as visibility dropped to near zero. Not reduced visibility, near zero, the kind of zero where you can't see the car in front of you until you're already into it. And if you pulled up NASA's Earth Observatory imagery from that week, you would have seen something that would have been alarming to anyone who knew what they were looking at. Plumes of dust visible from orbit, drifting east across the continent from a source region centered on the southern high plains of Texas and Oklahoma, exactly the same geography that produced the storms of 1935. Now here's what makes all of this strange. Not disturbing, not dramatic, just genuinely, intellectually strange. Every single one of the conditions being observed in the spring of 2026, the drought duration, the soil exposure, the ocean temperature patterns, the atmospheric circulation, the failure of soil conservation infrastructure, every one of them was described in scientific literature years ago as the specific, identifiable recipe for a dust bowl. Not a drought, not a bad dust season, a dust bowl, the thing itself. The researchers who cracked that code published their findings in the Proceedings of the National Academy of Sciences in 2009. That's 16 years ago. The science is not new. The warning is not new. So here is the question that this entire story is actually about, and I want to say it plainly before we go any further, because everything that follows is an attempt to answer it. If Washington has known for 16 years exactly what causes the Dust Bowl, not roughly, not theoretically, but precisely, with a peer-reviewed model that has been tested against historical data and validated, and every single ingredient in that recipe is now present across the southern plains, why is no one in the federal government willing to say out loud what is happening to American soil right now? That's the mystery, not the climate, not the dust, the response. Let me give you the full picture. because the pieces are scattered across a dozen different agencies and datasets and news cycles that never quite connect to each other, and the story only becomes clear when you see all of them at once. We're going to start with the science, not the current conditions, but the breakthrough that made the current conditions legible. Because before 2009, even the scientists didn't fully understand what had actually happened in the 1930s. The Dust Bowl was a known disaster with an unknown mechanism, and then 3 researchers changed that. We have a drought that has now lasted 6 consecutive years across Texas and Oklahoma, already longer than the early phase of the 1930s drought that preceded Black Sunday. We have ocean temperature patterns that match the documented trigger for the original Dust Bowl with a precision that should be making people very uncomfortable. We have soil conservation infrastructure that has been quietly, methodically reduced over the past 2 decades, removing the exact buffers that were installed after 1935 specifically to prevent a recurrence. And we have dust storms so large and intense they are being described using vocabulary imported from the Sahara Desert. The recipe is back, every ingredient is on the counter, and somewhere in a federal building, someone who understands what those ingredients mean together is choosing not to say it. That's where we're going. But first, we need to understand the recipe itself, because until you understand what was actually discovered in 2009, the current conditions look like bad luck. After you understand it, they look like something else entirely. Part 2. The 2009 breakthrough. That changed everything. For decades after the Dust Bowl ended, scientists argued about what had actually caused it. This might seem strange given that the disaster was so well documented. There are photographs, first-hand accounts, federal records, soil surveys, meteorological data going back to the early 1900s. The event was not mysterious in terms of its effects. It was mysterious in terms of its mechanism. Everyone could see what it did. No one could fully explain with scientific rigor why it happened when it did, why it was as severe as it was, and crucially, whether it could happen again. The 2 competing explanations that dominated the field for most of the 20th century were, roughly speaking, drought and farming. Either the Dust Bowl was primarily a climate event, a severe prolonged drought that happened to occur over a densely cultivated region, or it was primarily a land use event, the consequence of reckless ploughing that destroyed the native grass cover and left the soil exposed to wind. Both of these explanations had obvious evidence behind them. The drought was real and severe. The ploughing was real and extensive. But neither explanation, on its own, could fully account for the scale and duration of what actually occurred. If drought alone was the answer, then equally severe droughts in the same region before widespread cultivation should have produced similar dust events. They didn't, at least not at the same scale. If overploughing alone was the answer, then similar ploughing in regions without severe drought should have produced dust bowls too. They didn't, at least not with the same catastrophic feedback. The 2 explanations kept pointing at each other. Drought explains why the soil was dry, farming explains why there was no vegetation to hold it, but the combination, the specific amplification that turned a drought into a decade-long ecological collapse, remained scientifically unresolved. Then in 2009, Benjamin Cook, Ron Miller, and Richard Seeger published a paper in the Proceedings of the National Academy of Sciences that changed the way scientists understood what had happened. Cook was at NASA's Goddard Institute for Space Studies. Miller and Seeger were at Columbia University's Lamont Doherty Earth Observatory. Together, they ran a series of climate model simulations designed to isolate the contribution of different variables to the Dust Bowl severity. And what they found answered the old debate in a way that both sides had been partially right and partially wrong about. Their methodology involved running what are called general circulation models, the same class of computational climate models used for weather forecasting and climate projection, and systematically varying the inputs. They tested what happened when you fed the model the actual sea surface temperature patterns from the 1930s without the land degradation. Then they tested what happened when you added the land degradation back in. The results were striking in what they revealed about each variable's individual contribution. Sea surface temperatures alone, specifically the pattern of a cooler-than-normal tropical Pacific combined with a warmer-than-normal North Atlantic, produced significant drought over the Great Plains in the model. This confirmed that the ocean configuration was a real and substantial driver of the drying. The atmospheric mechanism is not complicated once you understand it. A cool tropical Pacific shifts the position of the jet stream, moving the storm track northward and creating a zone of sinking air over the southern plains. Sinking air suppresses rainfall. This is basic atmospheric physics, and the model captured it accurately. But here's what was so important about their finding. Sea surface temperatures alone did not reproduce the full intensity of the Dust Bowl. The model with ocean forcing and no land degradation produced a drought. It did not produce the Dust Bowl. The temperatures were wrong, the precipitation was wrong, the feedback wasn't there. Something was missing, and Cook, Miller and Seeger knew exactly what it was. When they added land degradation to the model, representing the large-scale removal of native vegetation across the high plains, the simulation transformed. Suddenly, the model reproduced temperatures matching the historical record. Suddenly, the precipitation deficit matched what had actually been measured in the 1930s. Suddenly, the feedback loop appeared, exposed soil releasing more heat into the atmosphere, dust aerosols altering the energy balance, the atmosphere responding to degraded land in ways that reinforced and extended the drought rather than allowing it to recover naturally. What Cook and his colleagues had demonstrated was that the Dust Bowl was not a drought with unfortunate timing. It was a coupled system failure, a climate forcing acting on a land surface that had been stripped of its natural resilience, producing an interaction that neither variable could have generated alone. The dust itself wasn't just a product of the drought, it was an active participant in sustaining and deepening it. That was the key insight that the separate cause explanations had both missed. In a companion paper published in Geophysical Research Letters in 2008, Cook had already begun quantifying the radiative forcing effect of dust, the way suspended particulate matter in the atmosphere absorbs and reflects solar radiation, altering surface temperatures and atmospheric stability in ways that feed back into precipitation patterns. The dust, once mobilized, was doing climate work. It was changing the system it had been created by. The Dust Bowl, in other words, had developed its own immune system against recovery. What this means for us, right now, today, in April 2026, is something that should stop you cold. The Dust Bowl is not a historical anomaly. It is not a product of unique circumstances that could never recur. It is a reproducible state of a system. A specific combination of ocean temperature patterns plus land surface degradation equals Dust Bowl. That's the equation. And if you can identify that equation from the historical record, you can also recognize when the variables are assembling again in the present. You can watch the recipe come together in real time, which is exactly what we are now able to do, and exactly what appears to be happening. So the question isn't whether we understand the mechanism. We do. The question is what we're doing about the fact that the mechanism's running again. Part 3. The ocean configuration has reappeared. There is a number that matters more than almost any other piece of data in this story, and it is called the Oceanic Niño Index. The National Oceanic and Atmospheric Administration maintains this index as its primary tool for tracking the state of the tropical Pacific Ocean, specifically whether sea surface temperatures in the central and eastern equatorial Pacific are warmer or cooler than the long-term average. A positive value means El Niño conditions, warmer tropical Pacific, wetter winters across the southern United States. A negative value means La Niña conditions, cooler tropical Pacific, drier winters across the southern United States. The magnitude of the departure from average tells you how strong the forcing is. Going into the winter of 2025 to 2026, the Oceanic Niño Index registered approximately negative 0.55 degrees Celsius, a weak La Niña state. By early spring 2026, that number had migrated toward negative 0.16, approaching what NOAA classifies as neutral territory. Now, to a casual observer, that transition from weak La Niña to near neutral might look like the situation improving. If La Niña causes drought and La Niña is weakening, surely the drought should weaken too. That is a completely reasonable assumption, and it is also, unfortunately, incomplete. Here's why. The Cook, Miller and Seeger research did not identify a strong sustained La Niña as the trigger for the Dust Bowl. It identified a specific pairing, a cool tropical Pacific combined with a warm North Atlantic. That pairing, as opposed to La Niña alone, is what the atmospheric models link to the specific drought pattern over the southern plains. And the reason that distinction matters in 2026 is that the second half of that pairing, the warm North Atlantic, is not weakening. It is, by multiple measures, at or near record levels. The North Atlantic has been running anomalously warm for an extended period. The specific mechanism by which a warm North Atlantic reinforces drought over the central United States is distinct from the Pacific mechanism but works in the same direction. While Pacific cooling shifts the jet stream northward and creates subsidence over the plains, Atlantic warming alters the temperature gradient that drives moisture transport from the Gulf of Mexico northward into the continent. When the Atlantic is unusually warm in certain configurations, it can actually suppress the northward flow of Gulf moisture that would otherwise provide rainfall to the plain states. The two ocean basins acting together create a kind of atmospheric pincer, the Pacific pushing the storm track away, the Atlantic reducing the moisture source. This exact configuration, cool or neutral Pacific, warm Atlantic, is what the 2009 paper identified as the oceanic fingerprint of the Dust Bowl, and this is not a rare configuration. Looking across the instrumental record going back to roughly 1880, researchers have identified somewhere between 8 and 12 occurrences of similar pairings over approximately 145 years of data. That means it happens roughly once every 12 to 18 years on average. It is not unusual. What is unusual is its combination with a land surface that has been simultaneously degraded. Because here is the important point from the Cook research. The ocean configuration creates drought. It does not by itself create a dust bowl. The drought has to find degraded land to work with. In years when the same ocean configuration occurred but the land was either in good condition or under protective cover, you got drought. You got dry years, you got agricultural stress. But you did not get the self-reinforcing feedback loop that produces catastrophic sustained dust mobilization. The ocean sets the table. The land determines whether the meal becomes a disaster. There's a question worth sitting with here, and I want to flag it honestly as something that scientists are actively debating rather than presenting it as settled fact. The North Atlantic has been warming on a multi-decadal trend that most climate researchers attribute, at least partially, to the accumulation of greenhouse gases in the atmosphere. If that trend continues, and there is no strong physical reason to expect it to reverse in the near term, does it mean that this particular ocean configuration becomes more persistent, more likely to recur, more likely to stay in place for longer once it establishes? We don't have a definitive answer to that question. What we do have is the observation that the configuration is currently present, that it matches the documented trigger for the original Dust Bowl, and that it is combining with drought conditions that have now persisted for 6 consecutive years. The ocean started this sequence, but the ocean is only half the story. The other half is under our feet, and it has been changing in ways that almost nobody noticed until the dust started moving. Part 4. The drought that quietly crossed the line. The United States Drought Monitor is a joint product of the National Drought Mitigation Center, NOAA, and the United States Department of Agriculture. It produces weekly maps of drought conditions across the continental United States using a classification system that runs from abnormally dry at the low end, through moderate, severe, extreme, and finally to exceptional, the most intense category, representing conditions so severe that they carry multi-year recovery timelines even after precipitation returns to normal. As of early April 2026, the Drought Monitor showed approximately 89% of Texas in some form of drought, with a substantial portion in the severe to exceptional range. Oklahoma was at approximately 99% drought coverage, nearly the entire state. The most drought-affected region of the entire country was centered on exactly the same geography as the Dust Bowl's epicenter, the Texas Panhandle, southwestern Oklahoma, southeastern Colorado, and the adjacent portions of Kansas and New Mexico. But the number that matters most is not the percentage of area in drought, it is the duration. The current drought across the southern high plains has now persisted for 6 consecutive years. 6 years! Consider that in historical context. The drought that preceded Black Sunday, the most catastrophic single dust event in American history, which occurred on April 14, 1935, built over roughly 3 to 4 years before that event. The current drought is already longer than the early phase of the 1930s drought. We are past the point where this can be described as a bad run of dry weather that will resolve on a normal seasonal timeline. 6 years of drought does not mean 6 years of below average rainfall that you recover from in one wet spring. It means 6 years of compounding soil moisture deficit, vegetation dieback, groundwater depletion, and surface crust destruction that progressively reduces the land's ability to absorb the rain it does receive and its resilience against the wind when it doesn't. This is a concept worth understanding clearly, because the relationship between drought duration and land vulnerability is not linear, it's exponential. In the first year of drought, perennial grasses go dormant. They don't die, they wait. Annual plants fail to germinate. Surface soil loses some moisture. In the second year, the perennials begin to thin. Root systems weaken. Soil structure starts to degrade. By the third year, substantial vegetation die-off is occurring. Root channels that previously allowed water infiltration collapse. Soil develops a hardened, sealed surface that sheds rain instead of absorbing it, which means that even when rain comes, it runs off rather than replenishing the profile. By year 4, 5 and 6, you are dealing with a fundamentally altered soil system. It is not a healthy soil in a drought, it is a degraded soil, and the distinction between those two things determines what happens when the wind picks up. The expansion pattern of the current drought is also significant. Eastern Colorado, which had been somewhat buffered from the worst conditions centered on the Texas and Oklahoma panhandles, saw rapid degradation in a very short window in April 2026, dropping a full drought category in approximately 1 week. That kind of rapid deterioration is not a gradual weather statistic shift. It's a system moving. It's the drought expanding its footprint at a pace that echoes the spread patterns documented in the historical record of the 1930s. Compounding the drought's soil impact is the role of wildfire. In the first quarter of 2026 alone, more than 1,100,000 acres burned across the Southern Plains region. Fire in this context is not just a disaster in itself. It is a soil preparation event for dust mobilization. Fire removes the remaining standing vegetation. It destroys the organic litter layer that helps bind soil particles. It can alter soil chemistry in ways that reduce its structural integrity. And then the wind arrives and finds a surface with no protection, no moisture, no roots, no cover, and the dust rises. Between 2020 and 2024, agricultural losses across the drought-affected region totaled approximately $23.6 billion. That number is enormous by any standard, but I want to resist the temptation to use it as merely an economic data point, because the more important thing it tells us is about the state of the system. $23.6 billion in losses means that the agricultural infrastructure of the Southern Plains has been operating in a state of sustained stress for years. It means that farmers are drawing down reserves, financial reserves, soil reserves, groundwater reserves, just to keep operating. It means the system is not in equilibrium, it is in managed decline, and the management tools that are keeping it from collapsing faster are themselves under strain in ways that bring us directly back to the central question of this story. Because the ocean configuration created the drought conditions, the drought has done its damage to the soil, but whether those conditions produce a dust bowl or merely a very bad drought depends on one more variable, the state of the land itself. And that variable, in 2026, is worse than most people realize. Part 5. The missing ingredient that isn't missing. In the 1920s and early 1930s, approximately 5.2 million acres of native sod, shortgrass prairie that had covered the high plains for thousands of years, its root systems extending 6 to 8 feet into the soil, its plant communities evolved over millennia to survive drought by going dormant rather than dying, were converted to cropland. The ploughing was rapid, mechanized, and financially motivated. World War I grain prices had made farming the plains enormously profitable. The drought hadn't started yet. The land looked productive. There was no reason, from a short-term economic perspective, not to plough. The native sod wasn't just vegetation, it was a structural system. Those deep root networks held soil particles together through physical binding. The organic matter in the root zone created aggregates, clumps of soil particles that resist wind erosion because their mass and internal cohesion make them too heavy and too interconnected to be easily mobilized by wind. When you plough native sod, you destroy those aggregates, you fragment the root networks, you expose the loose, individual soil particles that were previously bound inside a living matrix. You have not just removed a plant community, you have converted a stable surface into a potential dust source. And when drought arrives and kills off the crop cover, What you are left with is bare, loose, unprotected soil on a flat, windy landscape with nothing between it and the atmosphere. That is the historical story. Now here is the present tense version, and I want you to hold the comparison carefully in your mind. The Conservation Reserve Programme, commonly called the CRP, was established in 1985 specifically as a policy mechanism to remove fragile, erosion-prone farmland from active crop production and convert it back to vegetative cover, usually native grasses or other perennial plants suited to local conditions. It was, in structural terms, a partial reversal of what had happened in the 1920s. Not a complete reversal. The native sod ecosystem cannot be fully reconstituted on century timescales, but a meaningful buffer against wind erosion on the most vulnerable acres. At its peak, enrollment around 2007, the CRP had approximately 36.8 million acres enrolled nationally. By 2026, that enrollment had declined by approximately 11 million acres from the peak. 11 million acres. To put that in perspective, the total acreage of native sod that was ploughed in the run-up to the Dust Bowl was 5.2 million acres. The protective cover that has been removed from the CRP over the past 2 decades is more than twice that. Now, it is important to be precise here. CRP enrollment is not a direct one-to-one analogue for the sod ploughing of the 1920s. The land leaving CRP was not all in the southern plains. Not all of it was on the most erosion-vulnerable soil types. The situations are not identical, but the direction is the same. Land that was under protective vegetative cover has been put back into crop production. The reason for the decline is not mysterious. CRP rental rates, the payments the federal government makes to farmers to keep land enrolled, fell in real terms relative to the value of crop production on that land. When it becomes more economically rational to farm marginal land than to leave it enrolled in the CRP, farmers farm it. This is not a moral failure. It is a rational response to an incentive structure that was allowed to degrade. Then, there are the shelter belts. In response to the Dust Bowl, the Roosevelt administration funded the planting of what became known as the Great Plains Shelter Belt, a series of tree lines and windbreaks stretching from the Canadian border to Texas, designed to reduce wind velocity at the surface, trap blowing soil, and create microhabitats of moisture retention. Approximately 220 million trees were planted between 1935 and 1942. These were not decorative features, they were functional infrastructure. The physics of a shelter belt is straightforward. Trees create drag on the wind, reducing surface wind speed in a protected zone, extending downwind from the tree line at roughly 10 to 15 times the tree height. Reduced wind speed means reduced erosive capacity. The ability of wind to pick up and transport soil particles drops dramatically as speed decreases because the relationship between wind speed and erosive power is not linear. A 10% reduction in wind speed produces more than a 10% reduction in erosion. Since the 1990s, shelter belt removal across the High Plains has been documented by multiple university and USDA research groups. The driving force is the same mechanization dynamic that drove CRP withdrawal. Large-scale mechanized farming with GPS-guided equipment works more efficiently on fields without obstacles. Trees are obstacles. Removing them increases the operational efficiency of modern farm equipment. It also, as a side effect, removes the wind erosion protection those trees were providing. The Environmental Working Group and other agricultural policy organizations have documented this trend extensively, and the conclusion is consistent across their analyses. The protective infrastructure installed after the 1930s disaster has been quietly, methodically reduced. Add to this the role of federal crop insurance, and the picture becomes even more structurally concerning. Federally subsidized crop insurance compensates farmers for production losses, including losses caused by drought and wind erosion. This is not inherently problematic. It provides economic stability in a volatile industry. But the incentive structure it creates is worth examining carefully. A farmer who plants on marginal, erosion-prone land and suffers crop failure receives compensation. A farmer who enrolls that same land in the CRP and leaves it under grass receives a rental payment. When the crop insurance compensation exceeds the CRP rental rate, which market conditions have periodically made the case, the rational economic choice is to plant on the marginal land, expose it to erosion risk, and rely on insurance to cover the losses. The system, in other words, financially incentivizes exactly the land use pattern that makes Dust Bowl conditions more likely while underfunding the program specifically designed to prevent it. We have the ocean configuration. We have a 6-year drought. We have soil that is increasingly unprotected, vulnerable, and stressed. The second ingredient, the land degradation that the 2009 research identified as the necessary amplifier for turning drought into Dust Bowl, is not missing. It is present. And when both ingredients are present simultaneously, something happens that goes beyond arithmetic addition. The system begins to feed itself. Part 6. Dust is not a symptom, it's a force. Most people, when they think about the dust storms of the 1930s, picture them as the result of the Dust Bowl. The drought happened, the land dried out, the wind picked up, and dust was the visible, dramatic evidence of those conditions. That picture is accurate as far as it goes, but it is incomplete in a way that turns out to be critically important for understanding why the Dust Bowl lasted as long as it did, and why similar conditions today carry the same potential for sustained catastrophe. Dust is not a passive symptom. Once it is mobilized at sufficient scale, it becomes an active participant in the climate system, a feedback mechanism that doesn't just respond to drought, but actively works to perpetuate it. Here is the physics. Dust aerosols suspended in the atmosphere interact with solar radiation in two distinct ways. Fine dust particles scatter incoming sunlight back to space, which has a cooling effect on the surface directly beneath the dust plume. Coarser particles absorb solar radiation and convert it to heat, which warms the atmospheric layer where the dust is concentrated. The net radiative effect at the surface is a reduction in incoming solar energy, less sunlight reaching the ground. That sounds like it might help agriculture by reducing heat stress. But the atmospheric consequence is different. Warming in the mid-atmosphere combined with cooling at the surface stabilizes the atmospheric column. A stabilized atmosphere is one in which convection, the vertical mixing that produces rain-bearing clouds, is suppressed. Less convection means less rainfall. Less rainfall means more drought. More drought means more exposed soil. More exposed soil means more dust. The loop closes, and it runs in the direction of making things worse. Cook's 2008 work in Geophysical Research Letters was among the first to quantify this feedback in the context of the Dust Bowl specifically. The findings suggested that dust radiative forcing contributed meaningfully to the persistence of drought conditions, that the dust wasn't just a product of the dry conditions, it was an amplifier of them. The Dust Bowl in this understanding was not just a drought that happened to produce a lot of dust, it was a drought that created a dust feedback that helped sustain the drought. It became, in a real physical sense, self-sustaining. The magnitude of this feedback is one of the genuinely uncertain elements in the current scientific picture. Different modelling approaches produce different quantitative estimates of how much dust forcing contributed to drought persistence in the 1930s, and the exact numbers remain a subject of active research. But the directional finding that dust acts as a drought-sustaining mechanism rather than a neutral byproduct is robust across multiple independent analyses. What this means for the current situation is sobering. The dust events we are seeing in early 2026, the AQI 1400 in Lubbock, the Haboob warnings, the satellite visible plumes, are not simply indicators that conditions are bad. They are indicators that the feedback mechanism is operating. Every major dust mobilization event that crosses the threshold into sustained continental transport is doing atmospheric work. It is changing the energy budget over the region. It is suppressing convection. It is, in a small but physically real way, making the next drought day more likely than the one before it. The recipe that Cook and his colleagues identified in 2009 didn't just describe how to start a dust bowl, it described how a dust bowl once started sustains itself, and that mechanism is now active, which raises the question of how far the system is from the threshold where the feedbacks become self-reinforcing, at a scale we can no longer easily interrupt. Part 7. The return of continental-scale dust transport. On May 11, 1934, a dust storm originating in the northern plains swept eastward across the entire continent. By the time it reached the east coast, it had been carrying approximately 350 million tons of topsoil across 2,000 miles of American geography. Dust settled on ships in the Atlantic Ocean. It fell on Washington, D.C. Residents of Chicago watched their city dim at midday. New Yorkers found a layer of plain soil on their windowsills in the morning. The storm was large enough and carried enough material that it fundamentally altered the public and political understanding of what was happening in the Great Plains. It was the moment the Dust Bowl stopped being a regional agricultural story and became a national crisis. Continental-scale transport of that kind requires a specific set of conditions. You need a source region with a large area of exposed, loose, fine-grained soil. You need wind velocities at or above the threshold for particle mobilization, typically around 12 to 15 miles per hour at the surface for fine silt and clay particles, higher for coarser material. You need the atmospheric structure to carry the mobilized particles vertically into higher wind levels, where they can be transported long distances without settling back to the surface. And you need the source region to be large enough that the supply of material isn't exhausted before the atmospheric transport pathway can move it across continental scales. In early 2026, NASA satellite imagery was showing dust transport events that, while not yet reaching the scale of the 1934 storm, were demonstrating the same fundamental pattern. Material, originating in the Texas and Oklahoma Panhandle region, being carried eastward by prevailing atmospheric circulation into the central and eastern portions of the country. The source region was active, the wind was moving, the atmosphere was doing what it does. The question of whether we are approaching the threshold for events comparable to the great continental-scale storms of the 1930s is genuinely uncertain, and I want to be honest about that uncertainty rather than overstate the case. The conditions required for a 1934 scale event are extreme. The soil exposure would need to be substantially greater than what currently exists. The atmospheric setup would need to be exactly right. These events were rare even during the Dust Bowl itself. They did not happen every season. But here is what the current satellite record tells us. The source region is active in a way it has not been for decades. The storms being produced are large enough to be clearly visible from orbit. They're large enough to push air quality in major Texas cities above every threshold the EPA's index was designed to describe. The transport pathway, the atmospheric corridor that carries Great Plains material eastward, is functioning. We are not at 1934. The question the current data asks is not whether we could get there, but what would need to change to get us from where we are to where that becomes likely. And the answer, based on everything the 2009 research tells us, is not much. Continued drought, continued soil exposure, a strong synoptic wind event. The system is closer to that threshold than it has been at any point since the 1950s. And every major dust mobilization event we see now is a data point confirming that the mechanism is running, that the central thread of this story, the recipe is back and nobody's saying so, is not a theoretical concern. It is an observable physical reality. Part 8. AQI 1400. When measurement systems break. The EPA's Air Quality Index was designed to communicate health risks to the general public. The scale runs from 0, clean air, through various colour-coded tiers, reaching what the agency designates as hazardous, at values above 300, and extending to 500 at the top of the published scale. At 500, the guidance is unambiguous. Everyone should avoid all outdoor physical activity. Sensitive groups should remain indoors, and if you have respiratory conditions, you should be treating this as a medical emergency situation. Lubbock, Texas registered an AQI of approximately 1,400 during the March 2026 storm events. That number is not a different tier of the same scale. That number is operating in a range the scale was never designed to reach, because the designers of the scale were not planning for conditions that exceeded their worst-case scenario by a factor of nearly 3. The instruments were still functioning, they were measuring accurately. The problem was that the framework built to interpret their measurements had been constructed with an implicit assumption that American air quality, even at its worst, would stay within a certain envelope. Lubbock went outside that envelope. The health implications are not difficult to project from basic respiratory medicine. Particulate matter at those concentrations, particularly the fine PM 2.5 particles, which are small enough to penetrate deep into lung tissue, produces acute irritation of mucous membranes, bronchial inflammation, and in prolonged exposure, can trigger conditions analogous to what was documented in the 1930s as dust pneumonia. The 1930s, dust pneumonia was a real clinical phenomenon, an acute respiratory illness caused by the inhalation of fine soil particles that caused inflammation and fluid accumulation in the lungs. It killed people. It killed children in particular. The conditions in Lubbock in March 2026 were not identical to the conditions that produced dust pneumonia in 1935, but they were operating in the same physical regime. We are past the point of academic comparison. The system is producing measurable, classifiable extremes that exceed the frameworks we built to track them. That is, at its core, what this story is about. Part 9. Why Haboob is a red flag, not a curiosity. The National Weather Service is a federal agency staffed by professional meteorologists whose job requires precision. They don't borrow vocabulary from other regions and climate systems casually or for effect. When the NWS Amarillo office began issuing Haboob warnings for events on the southern plains, that word choice was not a dramatic flourish. It was a technical classification decision made by trained observers looking at what their instruments and their own direct experience were telling them about what kind of meteorological event they were dealing with. A haboob is specifically defined as a type of intense dust storm associated with collapsing thunderstorm outflows in arid desert environments. The term originates from the Arabic word for strong wind, and it entered English language meteorology through British colonial-era observations in Sudan. It subsequently became standard terminology for similar phenomena in the Sahara, the Arabian Peninsula, and the American Southwest, particularly in Arizona, where the Phoenix area experiences regular haboob events generated by the desert conditions of the Sonoran. The key elements of a haboob are a wall-like structure, high wind speeds generated by downdraft outflow, and sufficient loose, fine-grained material on the surface to be rapidly mobilized into a dense, moving dust mass. The Texas Panhandle and southern Oklahoma are not the Sonoran Desert. They are not the Sahara. They have never, historically, been the kind of environment that routinely generated Haboob-class events. The fact that NWS Amarillo, not NWS Tucson, not a desert weather office, but the office responsible for agricultural plains country, is now using this vocabulary is a direct meteorological statement. The surface conditions on the southern plains have changed enough that the event types being observed there now match the event types associated with desert environments. The operational forecasters, the people closest to the actual atmospheric conditions, have adapted their language to match a physical reality shift that policy and public discourse has not yet acknowledged. That gap between what the people watching the sky are saying and what the people making decisions are doing is itself part of the story. The forecasters are telling us the system has moved. The question is whether anyone in a position to act is listening. Part 10. Fire, dust and wind are now coupled. One of the differences between the current situation and the 1930s that sometimes gets cited as a reason for cautious optimism is the difference in vegetation structure across the southern plains. The argument goes roughly like this. In the 1930s, the catastrophic ploughing had removed native sod and replaced it with annual crops on millions of acres, leaving essentially no perennial root structure across huge stretches of the landscape. Today, even on degraded land, there is typically some residual vegetation. Not healthy, not resilient, not native, but some coverage. The comparison is accurate as far as it goes. What it does not account for is wildfire. In the first quarter of 2026 alone, more than 1,100,000 acres burned across the southern plains. The fires were driven by the same conditions producing the dust: extreme drought, low humidity, strong winds, and the accumulation of dry, dead vegetation that drought had killed but not yet removed from the landscape. The fire conditions were, by any historical measure, extraordinary. Here is why wildfire matters to the Dust Bowl question. Fire removes the residual vegetation that drought had weakened but not fully killed. After a fire burns through an area, the organic surface layer, the litter of dead plant material, fungal networks, and partially decomposed organic matter that binds soil particles and maintains aggregate structure, is destroyed. What remains is mineral soil with minimal binding, minimal moisture, minimal protection. It is, in the relevant physical sense, indistinguishable from ploughed ground. The wind doesn't know the difference between a field that was ploughed last season and a field that burned last month. In both cases, it finds loose, unprotected, fine-grained material sitting at the surface with nothing to hold it down. The feedback loop this creates is distinct from anything that operated in the 1930s, and it potentially runs faster. Fire destroys vegetation, which exposes soil for dust mobilization. Dust mobilization alters the atmospheric energy budget, suppressing rainfall, which intensifies drought. Drought kills vegetation, creating fuel loads for more fire. Fire burns that fuel, exposing more soil. The cycle can accelerate in a way that the purely drought plus ploughing dynamic of the 1930s could not, because fire can remove protective cover in hours that drought takes months to kill, and the fire season in 2026 is happening during the same drought that is already stressing the soil across the same region where the ocean configuration and land degradation are already in place. The recipe that Cook and his colleagues identified in 2009 was constructed from the variables that existed in the 1930s. The current system appears to have added an additional amplification pathway that the original recipe didn't include, which raises an uncomfortable possibility. If the 1930s configuration was sufficient to produce Black Sunday and a decade of catastrophic dust events, what does a version of that configuration with an additional fire-dust drought feedback loop produce? We don't have historical precedent for that question. We may be developing it in real time. And none of this is being said clearly by any federal agency, which brings us to the part of the story that goes beyond climate and agriculture into something more structural and more difficult to explain. Part 11. The Ogallala Illusion. There is a reason the Texas Panhandle and the adjacent high plains of Oklahoma, Kansas, Colorado, and New Mexico remain some of the most intensively farmed territory in the United States, despite experiencing the worst sustained drought in the country. It is not resilience. It is not a naturally well-watered landscape making the best of a temporary dry spell. It is the Ogallala Aquifer, a massive underground freshwater reservoir stretching beneath approximately 174,000 square miles of the Great Plains, from South Dakota to the Texas Panhandle, and containing more water than Lake Huron. Since the mid-20th century, the agriculture of the High Plains has been substantially supported by pumping from this aquifer, providing irrigation that allows crops to survive even when surface water conditions are catastrophic. The Ogallala is, in the relevant sense, the reason that the southern plains looks more stable right now than the 1930s landscape did. Irrigated agriculture can survive drought conditions that rain-fed agriculture cannot. The green fields visible on satellite imagery in the middle of a 6-year drought exist because water is being pulled from thousands of feet underground and applied to the surface. The system appears functional, the soil appears productive, the farms appear to be operating. What the surface appearance conceals is the rate of depletion. The Ogallala recharges extremely slowly, on the order of fractions of an inch per year in most of the high plains, reflecting the low natural precipitation of the region. The rate at which it is being pumped for irrigation exceeds the recharge rate by a factor estimated at roughly 800% in some parts of the Texas Panhandle. The aquifer is not being used as a resource, it is being mined. And like any finite deposit being mined faster than it replenishes, it is declining. In the southern high plains, particularly the Texas Panhandle, the epicenter of the current drought, and the historical epicenter of the Dust Bowl, some areas are estimated to have less than 25 years of usable irrigable water remaining at current extraction rates. Some areas have already passed that threshold. Wells that reached water at 60 feet in the 1950s now require drilling to 300 feet or more. Pumping costs have increased dramatically as the water table drops, making marginal irrigated agriculture progressively less economically viable. This matters to the Dust Bowl question in a specific way. The Ogallala is not a solution to the underlying conditions. It is a delay mechanism. It's allowing agriculture to continue on land that would otherwise have already crossed the threshold into the kind of bare, abandoned, unprotected condition that the 1930s drought produced through different means. But the delay has a timeline. When the irrigated agriculture of the Texas Panhandle can no longer be sustained by aquifer water, whether because the water is gone, or because pumping costs make it uneconomical, or because drought-related policy changes restrict extraction, the land that has been maintained under crop cover by irrigation will lose that cover. And it will lose it rapidly, because the transition from irrigated cropland to unprotected bare soil does not happen gradually. It happens when a farmer stops pumping, which can happen in a single season. The 1930s didn't have this variable. The agriculture of the Dust Bowl era was rain-fed. When the rain stopped, the crops failed, the land was abandoned, and the surface was exposed. The current system has a buffer, but the buffer is temporary. It is shrinking, and the system it is buffering does not become more resilient as time passes. It becomes more vulnerable. The Ogallala is not saving the high plains from a dust bowl. It is making the eventual transition to dust bowl conditions more abrupt when it comes. An illusion of stability is, in certain respects, more dangerous than visible instability, because it postpones the recognition of the problem until the solutions become more expensive and the collapse becomes more sudden. Part 12. The warmer baseline problem. The 1930s. Dust bowl occurred during a period when global average surface temperatures were already elevated relative to the pre-industrial baseline, but at a level dramatically lower than the present. The best estimates from paleoclimate reconstructions and instrumental records put global average temperatures during the Dust Bowl era at roughly 0.1 to 0.3 degrees Celsius above the pre-industrial average. By 2026, that number is approximately 1.3 to 1.5 degrees Celsius above pre-industrial levels, roughly 5 times higher. This matters because temperature directly controls the physics of drought. Warmer air holds more water vapor at saturation. This is basic thermodynamics, described by the Clausius-Clapeyron relationship, and warmer air has a higher evaporative demand. What this means practically is that a given precipitation deficit produces more severe drought under a warmer baseline. The same amount of rainfall that in the 1930s would have maintained marginal soil moisture now evaporates faster, leaves less residual moisture in the soil profile, and produces measurable drought symptoms more quickly. The drought doesn't have to be deeper to be more damaging. It just has to occur in a warmer atmosphere. The calculation here is not speculative. Scientists quantify this effect using what is called the Palmer Drought Severity Index, which incorporates both precipitation and temperature in its drought assessment. When you apply current temperature levels to historical precipitation deficits, the resulting PDSI values are consistently more extreme than the same precipitation deficit would have produced in a cooler climate. The current 6-year drought across the southern plains is occurring in an atmosphere that is substantially warmer than the atmosphere of the 1930s. The same drought in physical terms hits harder. There is an important nuance to maintain here, and I want to be precise about it because this point is frequently garbled in public discussion. Climate change is not the cause of the current conditions. The ocean configuration, the cool Pacific, the warm Atlantic, is the primary driver of the drought, and that configuration has occurred multiple times in the instrumental record under climate conditions far cooler than today's. Land degradation has been occurring since the 1980s for economic and policy reasons that are not primarily driven by global temperature. The Dust Bowl recipe does not require climate change to operate. What climate change does is amplify the recipe. It takes a drought that the ocean configuration would produce anyway and makes it hit harder. It takes exposed soil that land use policy has left unprotected and makes it lose moisture faster. It takes a feedback loop that the Cook research identified as self-sustaining and gives it a more favourable background state to operate in. The warmer baseline problem is not the origin story, it is the amplifier. And in a system that is already operating close to a critical threshold, an amplifier that increases the intensity of every variable in the recipe is not a minor factor. It is the difference between a close call and a disaster. Part 13. Population in the dust zone. The 1930s. Dust Bowl displaced approximately 2.5 million people from the Southern Plains region. The migration that Steinbeck documented in The Grapes of Wrath, the exodus of the Okies and the Arkies along Route 66 toward California. That displacement was catastrophic on human terms, but it occurred across a landscape that was, by modern standards, sparsely populated. The Great Plains in the 1930s was agricultural country, small towns, farm communities, a rural population distributed across a large area with relatively low density in most of it. The present-day High Plains and surrounding region includes major metropolitan areas. Lubbock, Texas has a population of approximately 260,000 people. Amarillo is over 200,000. Oklahoma City, which sits in the drought zone, has more than 600,000. These cities were smaller or non-existent in their current form during the Dust Bowl era. The infrastructure they depend on, highways, airports, power grids, water treatment facilities, was not designed or stress-tested against conditions like AQI 1400 near-zero visibility multi-vehicle crashes and sustained contamination of air intake systems with fine silicates. The public health implications of the current dust events scale with population in a straightforward way. More people breathing the same degraded air means more acute respiratory events, more emergency room visits, more lost school and work days, and more cumulative long-term lung damage. The economic disruption from the current storms, flight cancellations, highway closures, agricultural equipment damage, operates across a more complex and densely interconnected infrastructure system than existed in the 1930s. And the psychological and social impact of watching your city disappear into a brown wall of dust is not trivial. The same recipe, in the same geography, now has a much larger human population inside its operational footprint. That doesn't change the climate science, but it substantially changes the consequence calculus. Part 14. The Collapse of Institutional Memory. On April 14th, 1935, Black Sunday, a dust storm of exceptional scale swept across the southern plains, reducing visibility to zero across a region hundreds of miles wide and driving thousands of tons of topsoil into the atmosphere. The storm was not unusual in the context of what the region had been experiencing for 3 years. What was unusual was its size, its intensity, and the fact that it hit on a Sunday afternoon when people were outside, not sheltered in their homes or workplaces. The photographs from that day, walls of dust taller than buildings, people running for their lives from a moving brown apocalypse, became iconic. They shocked the country. But here is what matters more than the shock. The response that followed was extraordinarily fast by any standard of government action. The Soil Conservation Service was created later in 1935, within months of Black Sunday. Hugh Hammond Bennett, who had been warning about soil erosion for years before the Dust Bowl confirmed his predictions, was appointed its first chief and moved with unusual urgency to deploy every tool available. The Great Plains Shelter Belt was funded and operational within 2 years. The Conservation Reserve concept, paying farmers to take fragile land out of production, was developed and began implementation within a few years. Emergency soil surveys, erosion mapping, and farmer education programs were stood up across the affected region in a fraction of the time that comparable federal programs typically require. The speed of that response reflected 2 things: the physical visibility of the crisis and the fact that the people in policymaking positions in 1935 had personal living memory of the problem and had watched it develop in real time. FDR's administration included agricultural officials who had been directly engaged with soil erosion issues for years. The scientific understanding, while incomplete by modern standards, was sufficient to identify the mechanism and the solution, and critically, there was political will to act at a scale commensurate with the problem. By 2026, the institutional memory of the Dust Bowl is essentially generational history. The people who experienced it are gone. The policy infrastructure it created, the Soil Conservation Service, which was later reorganized into the Natural Resources Conservation Service, the CRP, the Shelter Belt programs, has undergone multiple decades of budget cycles, administrative reorganizations, and political shifts that have progressively reduced its scale and influence. The CRP enrollment decline we discussed earlier is part of this pattern. Not a sudden policy reversal, but a slow erosion of commitment driven by competing budget priorities, changing agricultural economics, and the absence of anyone in the room who remembers why those programs were built in the first place. The Environmental Working Group has documented the trend in federal agricultural conservation spending over recent decades, and the picture is consistent. In real terms, the programs designed to prevent a recurrence of the Dust Bowl have been systematically underfunded relative to the programs designed to compensate farmers after losses occur. The balance has shifted from prevention to response. And the irony at the core of this shift is that the scientific understanding of what prevention requires has never been better. The 2009 research gave policymakers a precise, validated model of how the system fails. The data systems, drought monitoring, satellite imagery, ocean temperature tracking, give current officials real-time visibility into whether the conditions identified in that model are assembling. The tools to recognize the risk exist. What has eroded is the institutional will to use them at the scale the risk requires. There is a concept in organizational behavior called collective memory, the shared knowledge and learned responses embedded in institutional structures over time. The Soil Conservation Service was a carrier of collective memory about the Dust Bowl. It embodied the lessons learned at enormous human cost across the 1930s, and it translated those lessons into operational programs, staffing patterns, and budget allocations that persisted for decades. The progressive restructuring and reduction of that agency, and the parallel weakening of the programs it administered, represents a form of institutional forgetting. The knowledge exists in libraries and papers. The capacity to act on it at scale does not exist in the same way it did in 1950, or 1960, or 1975. That gap between what we know and what we have preserved the capacity to do about it is not an accident of history. It is the result of specific policy choices made across multiple administrations, and it is directly relevant to the central question of this story, which is not why the conditions are occurring, but why the response is not. Part 15. Insurance versus prevention. The federal crop insurance program is one of the largest and most politically durable elements of United States agricultural policy. In a typical year, the federal government subsidizes approximately 60% of the premiums farmers pay for crop insurance, with total federal outlays in the range of $8 to $10 billion annually. The program provides farmers with income protection when crop yields fall below a threshold level, covering losses from drought, flood, pest damage, and other covered perils. It is popular with farmers, politically supported across the agricultural states, and deeply embedded in the farm economy. The program is also, in its current structure, one of the most significant drivers of the land use incentives that are contributing to the conditions this story is about. Here is the mechanism. Crop insurance does not, in most of its forms, require participating farmers to follow soil conservation practices as a condition of coverage. A farmer can plant highly erodible land, soil type classifications that federal agencies have themselves identified as among the most vulnerable to wind and water erosion, and receive federal premium subsidies without committing to any erosion control measures. When that crop fails, the insurance pays out, the farmer is compensated, the land remains exposed, unprotected, and vulnerable to the next drought year. The cycle repeats. The Conservation Reserve Program, by contrast, pays farmers to not plant, to leave the land under grass or other protective cover, to preserve the soil structure and vegetation that makes the land resistant to wind erosion. The CRP payment is a rental rate, $1 per acre per year to keep the land enrolled. The economics of enrollment depend on whether that rental rate exceeds the expected return from farming the land, including the insurance backstop. In recent years, for a significant portion of highly erodible land in the southern plains, the crop insurance backstop has made farming marginal land more financially attractive than CRP enrollment. This is not a secret. Agricultural economists have written about this dynamic extensively. The Government Accountability Office has noted it. Conservation organizations have argued for addressing it. The policy response has been limited. The result is a federal agricultural support system that, taken as a whole, financially incentivizes putting vulnerable land into crop production, and then financially compensates the farmer when the vulnerable land fails, while the soil itself continues to degrade. Contrast this with the policy approach that followed the Dust Bowl. The 1930s response was not primarily about compensating farmers for losses. It was about preventing losses by changing what was happening on the land. The Soil Conservation Service wasn't writing checks to farmers whose fields had blown away. It was sending technical staff onto those farms to demonstrate contour ploughing, establish cover crops, plant shelter belts, and develop conservation plans that would prevent the fields from blowing away in the first place. The incentive structure was prevention-oriented. The money flowed toward actions that reduced vulnerability, not actions that compensated for it after the fact. The shift from a prevention-oriented to an insurance-oriented federal agricultural policy is not unique to the United States. It reflects a broader ideological shift across multiple decades toward market-based mechanisms and away from prescriptive land management requirements. That ideological shift has many legitimate arguments behind it, but it has produced a specific practical outcome in the context of Southern Plains agriculture. The land is more exposed than it would be under a prevention-oriented regime, and the cost of that exposure is being socialized through insurance payouts, rather than prevented through conservation investment. The tab for the next Dust Bowl, in other words, is already partially open. The question is how large it will grow before the policy calculus changes, and that depends, in part, on a political and institutional decision that has not yet been made, the decision to say clearly and publicly what is actually happening. Part 16. Why no one is calling it a Dust Bowl. Let's spend some time with the central question directly, because it deserves more than a rhetorical gesture. The science is clear, the conditions are documented, the comparison to the historical mechanism is explicit in the peer-reviewed literature, and yet, as of April 2026, no major federal agency, not NOAA, not the USDA, not the EPA, not the National Drought Mitigation Center, has issued a statement using the words Dust Bowl to describe the current situation. No senior administration official has held a press conference drawing the explicit comparison. No congressional hearing has been convened around the question of whether the conditions that caused the Dust Bowl have reassembled. Why? I want to offer several serious explanations for this, rather than a simple one, because I think the reality is genuinely more complicated than any single answer captures. The first explanation is institutional fragmentation. The data that, assembled together, tells the Dust Bowl story is distributed across multiple agencies with different mandates, different communication cultures, and different political reporting chains. NOAA tracks ocean temperatures and drought. The USDA tracks agricultural losses and CRP enrollment. The EPA tracks air quality. The NASA Earth Observatory produces satellite imagery. The Natural Resources Conservation Service tracks soil erosion. Each of these agencies sees its piece of the picture clearly. None of them has an explicit mandate to assemble the pieces into the integrated narrative that Cook and his colleagues published in 2009. The academic researcher has more freedom to say what the data collectively means than the agency official does. The second explanation is economic and political risk management. Agricultural commodity markets are sensitive to narrative framing. If the federal government officially declares that Dust Bowl conditions are present across the southern plains, that declaration carries implications for crop insurance, land values, commodity prices, and agricultural lending that could trigger market responses independent of the actual physical conditions. There is a real legitimate concern in agricultural policy circles that words matter, that labeling a situation can sometimes accelerate the dynamics the label describes. Whether that concern is sufficient justification for silence in the face of serious risk is a different question, but it is a real factor in the institutional calculus. The third explanation is liability and response obligations. If the federal government acknowledges that Dust Bowl conditions are present and that the federal crop insurance program and CRP funding structure are contributing factors, there is at minimum an implicit obligation to do something about it at scale commensurate with the acknowledgement. Acknowledging a Dust Bowl is not a neutral speech act. It creates political pressure for a response, and the response required by the scale of the problem, a major, funded, rapidly deployed soil conservation mobilization, analogous to what happened in 1935 and 1936, is expensive, politically complex, and would require reversing policy directions that have been in place across multiple administrations. The fourth explanation is the event versus system distinction in media and political framing. Modern news cycles and political communication are structured around discrete events. A specific storm, a specific crash, a specific fire, a specific quarterly loss figure. The Dust Bowl story, as the Cook research defines it, is a story about a system state, not an event. It is about a set of interacting conditions that have moved into a configuration associated with catastrophic outcomes. That kind of story is harder to cover, harder to communicate, and harder to act on than a single dramatic event that demands a response. The Haboob warning and the AQI 1400 are events. The reassembly of the Dust Bowl recipe is a system condition. Public and political attention systems are better designed to respond to the former than the latter. Put all of these explanations together, and what you get is not a conspiracy of silence, not a deliberate suppression of information by identifiable bad actors, but a structural silence, the product of fragmented institutions, misaligned incentives, risk-averse communication cultures, and the inherent difficulty of getting political systems to respond to system-level risks rather than event-level shocks. The knowledge exists, the data exists, the framework for understanding what it all means was published 16 years ago, and the system is not responding at scale, not because no one knows, but because the way the system is organised makes it very difficult for the knowledge to translate into action before the event arrives that finally makes the cost of inaction undeniable. That dynamic, the gap between knowledge and action, is the real story, and understanding that gap is the first step toward closing it. Part 17. Debunking the wrong explanations. Anytime conditions become alarming enough that official channels stop providing satisfying explanations, alternative explanations proliferate. This is as true for dust storms as for anything else, and honestly, it makes sense. When you watch a city of 260,000 people disappear into a brown wall at midday, and the federal response amounts to a drought monitor update and a quietly issued haboob warning, your brain starts looking for a story that matches the scale of what you're seeing. I understand that impulse completely. But here is the thing. Getting the explanation wrong does not just lead to bad conclusions, it leads to bad responses. And in a situation where the right response is already running dangerously late, the wrong explanation is not harmless, it is costly. So let me work through a few of the explanations that have circulated and explain why they are insufficient. Not to dismiss the people asking questions, because the questions themselves are legitimate. But because the correct explanation already exists, it is sitting in peer-reviewed literature, and it points directly towards solutions that we could actually deploy if enough people understood what was really happening. The weather modification theory comes up every time drought and atmospheric anomalies converge, and I want to give it a genuinely serious answer, rather than a dismissive one, because the kernel of fact inside it is real. Atmospheric modification technologies do exist. Cloud seeding is a real, documented, actively used practice. Dozens of state and local agencies in the American West use silver iodide dispersal to attempt precipitation enhancement over watersheds and reservoirs. The United Arab Emirates runs one of the most sophisticated national cloud seeding programs in the world. China has invested billions in weather modification infrastructure. The technology exists, it is deployed, and governments are not always transparent about where and when they use it. That part of the premise is accurate. Here is where the theory breaks down, and it breaks down on physics rather than politics. The energy scales involved in producing what we are currently observing across the southern plains, a 6-year multi-state drought pattern driven by specific ocean temperature configurations, compared to the energy scales of any existing or even theoretically plausible atmospheric modification technology, differ by approximately 10 to 12 orders of magnitude. I want to make sure that number lands properly. An order of magnitude is a factor of 10. 10 orders of magnitude is 10 billion times. 12 orders of magnitude is 1 trillion times. The ocean temperature anomalies that are driving the current atmospheric circulation pattern involve the redistribution of thermal energy across millions of square miles of ocean surface to depths of hundreds of meters across timescales of months to years. The total energy involved in that redistribution dwarfs the output of every power plant, every ionospheric heater, every cloud seeding aircraft, and every other human-operated atmospheric intervention system on Earth combined by a factor that is genuinely difficult to visualize. This is not a technology problem. It is not a funding problem. It is not a secrecy problem. It is a climate physics problem. The ocean is doing what the ocean does, driven by thermodynamic processes that operate at planetary scale, and no technology currently operated by any known actor can produce or sustain forcing at that scale. When someone tells you the drought is manufactured, the correct response is not to argue about government intentions, it is to ask them to account for the energy budget. The numbers close the case. The second explanation, the claim that what we're seeing is simply within the normal range of plains weather variability, that this is a bad dry spell but not something that warrants the kind of concern this story is articulating, is contradicted not by any single dataset but by the convergence of all of them simultaneously. And this is an important distinction, because individual datasets absolutely can be cherry-picked to support almost any conclusion you want to reach. A single year of below-average rainfall is normal. A single haboob event in the Texas Panhandle, while unusual, is not impossible. A single season of elevated CRP withdrawals is an agricultural policy story, not a crisis. Taken individually, any one of these data points can be rationalized as within the envelope of historical variability. What cannot be rationalized that way is all of them appearing together simultaneously, tracking in alignment with the specific multivariable recipe that Cook, Miller, and Seeger identified in 2009 as the documented mechanism of the Dust Bowl. 6 consecutive years of drought. Multi-decade low CRP enrollment, record North Atlantic temperatures, active La Niña to neutral Pacific transition, above-index air quality events that broke measurement instruments, haboob-class storm classifications in agricultural country. satellite visible continental-scale dust transport from the same source region as the 1930s. The probability that this specific combination of variables assembles by random coincidence at the exact time when the ocean configuration matches the Dust Bowl trigger pattern is not a matter of opinion or interpretation. It is a statistical argument that does not survive scrutiny. Each variable has occurred before in isolation. The pattern they are forming together has a known name, a known mechanism, and a known historical outcome. Normal variability does not produce this alignment. The Dust Bowl recipe produces this alignment because that is what we are looking at. The third explanation is in some ways the most interesting one, because it comes from the right direction but goes too far and ends up in the wrong place. The climate change's sole cause argument, the framing where everything visible in the southern plains right now is attributed to global warming full stop, is not wrong about climate change's role. It is wrong about climate change's primacy. As I described earlier in this story, the warmer baseline is an amplifier. It makes every drought more intense, every soil moisture deficit more severe, every feedback loop more energetic. Climate change is real, it is measurable, and it is making the current situation worse than the same conditions would have been 50 years ago. But climate change did not create the ocean configuration that is driving the drought. That configuration has occurred throughout the instrumental record across climate states cooler than today's, and it will continue to occur on multi-year cycles regardless of what happens to global average temperature. Climate change did not remove 11 million acres from the Conservation Reserve Programme. That was agricultural policy. Climate change did not dismantle the shelter belt infrastructure planted after 1935. That was mechanised farming economics and budget decisions. Climate change did not structure the federal crop insurance programme in a way that incentivises planting on marginal land. That was legislative choice. The land degradation that converts drought into Dust Bowl, the second ingredient in the recipe, the one without which the ocean forcing produces a drought but not catastrophe, is driven by specific, identifiable, reversible human decisions that have nothing to do with atmospheric carbon concentrations. This distinction matters enormously for the question of what we do about it. If the story is climate change caused this, the response timeline is a 20 to 30 years decarbonisation project involving global coordination, massive infrastructure investment, and political consensus that has proven extremely difficult to achieve. That response is important and necessary for 100 other reasons, but it will not protect a single acre of Texas topsoil this spring. If the story is the Dust Bowl recipe is reassembling, and we can interrupt it by restoring CRP enrollment, reinforcing shelter belt infrastructure, and realigning crop insurance incentives toward conservation, the response timeline is a farm bill cycle. The tools exist, the programs exist, the institutional capacity, however reduced, still exists. The response is available now at a cost that is a fraction of the damage it would prevent if the diagnosis is accurate. Getting the explanation wrong does not just produce incorrect understanding, it forecloses the most actionable solution at exactly the moment when action is most needed. The recipe is known, the ingredients are present, the one thing still missing is the willingness to call it what it is and respond accordingly. Part 18. Could Black Sunday happen again? April 14th, 1935. That date marks what meteorologists and historians call Black Sunday, the single most severe dust event of the Dust Bowl era, and one of the most extreme meteorological events ever recorded in North American history. But before I tell you what happened that day, I want you to understand something about the weeks leading up to it, because the storm itself lasted hours, and the conditions that made it possible had been building for years. By April of 1935, the southern high plains had already endured 5 consecutive years of below-average rainfall. The native grass that had held the soil together for thousands of years was gone across millions of acres, replaced first by wheat fields, then by nothing at all when the wheat failed and the farmers couldn't afford to replant. The topsoil was loose, dry, and sitting on a flat open landscape with no windbreaks, no root systems, no moisture to give it any cohesion whatsoever. The land had been, in the most literal physical sense, prepared. It was waiting for the right wind. On April 14th, the wind arrived. The storm originated in the northern plains and swept southward and eastward. driven by a powerful cold front with surface winds gusting to 60 miles per hour. It travelled as a wall of dust approximately 800 miles wide and several miles high, moving at roughly 60 miles per hour across the landscape. People who witnessed its approach described it as a moving cliff, a vertical brown-black wall that extended from the ground to as high as they could see, advancing toward them faster than they could run. Within minutes of the storm's arrival, noon became night. Not a dim, overcast afternoon. Night. Visibility dropped to zero. Absolute zero. Drivers abandoned their cars on the road because there was no longer any point in driving. They could not see the hood of their own vehicle. Animals suffocated in fields. People caught in the open were blinded and disoriented, some crawling on hands and knees trying to follow fences back to shelter. Inside homes, dust came through every gap, every crack, every keyhole. Families stuffed wet rags around their doors and windows and sat in the dark listening to the wind and waiting. The colour of the sky that day, described by witnesses as black, as brown-black, as the colour of death, as something that had no name in ordinary experience, became the defining image of the entire Dust Bowl era. It is the image that still comes to mind when people who know their history hear the words Dust Bowl. Not the poverty, not the migration, the sky. Woody Guthrie was in Pampa, Texas that day. He watched the storm approach and wrote a song about it that he called So Long, It's Been Good to Know Ya. A federal government photographer named Arthur Rothstein captured images of families running from the wall of dust that became some of the most reproduced photographs in American history. A young journalist named Robert Geiger, who had been travelling through the region, sent a dispatch back east that was the first recorded use of the phrase Dust Bowl in print. The storm did not just happen, it named an era. Now, the conditions that produced Black Sunday were, in retrospect, not exotic or mysterious. You needed a large area of exposed, loose, fine-grained soil, which the years of drought and aggressive ploughing had provided across millions of acres. You needed a strong frontal boundary generating high surface wind speeds, which the synoptic weather pattern of April 14th provided in abundance. You needed dry atmospheric conditions in the air column above the source region, conditions that would prevent the mobilized dust from being washed out by precipitation before it could travel hundreds of miles, which a 6-week dry spell across the region had provided. And you needed a source region large enough and with a high enough density of exposed material to supply the storm's mass at a rate that could sustain its structure over the full transport distance. The degraded high plains provided that in quantities that exceeded anything the storm needed. The prerequisites were not complicated. They were just terrible in combination, and they had been assembling, visibly and documented for years before the storm arrived. Can those conditions reassemble in 2026? I want to answer this carefully and honestly, because this is the kind of question where both overstatement and understatement carry real costs. Overstate it, and you produce panic that discredits the legitimate concern. Understate it, and you reproduce the exact error that left people unprepared on April 14, 1935. So here is the precise, accurate answer. Not all of the Black Sunday prerequisites are currently present at the scale they existed in 1935, and that distinction matters. The soil exposure across the southern high plains today is substantial and growing, but it is not yet at the same coverage percentage as the ploughed and abandoned landscape of April 1935. Perennial vegetation, however stressed and diminished by 6 consecutive years of drought, however damaged by the 1,100,000 acres of wildfire that burned in the first quarter of 2026 alone, still provides partial cover over a meaningful portion of the landscape. It is not healthy cover, it is not resilient cover, but it is cover, and cover matters at the margins of these calculations. Additionally, the atmospheric setup required for a Black Sunday class event, a specific combination of frontal timing, trajectory, wind speed and atmospheric dryness, is not something that assembles every spring. It assembled once in a decade of Dust Bowl conditions. It requires the right synoptic pattern at the right moment over the right source region. That combination is relatively rare even when the background conditions are favourable. Here is what I need you to understand about rarity in this context though, because this is where the statistical reasoning becomes critical and where intuition can lead you in exactly the wrong direction. Black Sunday was the most extreme event of the Dust Bowl decade. By definition, it was rare. It sat at the far end of the distribution of possible outcomes under Dust Bowl conditions, but its rarity did not mean it was unforeseeable. It did not mean the conditions that made it possible were absent until the moment it occurred. Those conditions had been present and building for years. What was absent was a specific triggering event, the right cold front on the right day, that finally realized the potential that the landscape had been accumulating. The event was rare. The vulnerability that made it possible was not rare. It was pervasive and persistent and documented and ignored. The current data tells us that the distribution of possible outcomes across the southern plains has shifted in the same direction it shifted in the early 1930s, toward higher probability of extreme events. The tail of the distribution is fatter, not because Black Sunday is imminent or inevitable, but because the background conditions that elevate the probability of Black Sunday class events are increasingly present. 6 consecutive years of drought have brought soil moisture levels and vegetation cover closer to the threshold required for large-scale dust mobilization. More than 1 million acres of wildfire in 3 months have stripped protective cover from land that drought had already weakened. CRP withdrawals have returned fragile, highly erodible acres to active production. The spring frontal systems that generate the necessary wind events will arrive as they do every year, because the atmosphere does not wait for us to be ready. The honest probability statement is not, Black Sunday will happen this spring. The evidence does not support that claim, and making it would be irresponsible. The honest probability statement is, the conditions that made Black Sunday possible are more fully assembled right now than at any point in the past several decades, and the probability of an event in that class is measurably higher than it was 10 years ago, or 20 years ago, and it is continuing to increase as long as the underlying conditions continue to develop. That is the statement risk assessment requires, not certainty, not a specific date, a shift in the probability distribution toward outcomes that carry catastrophic consequences if they occur. There is a version of the 1930s where someone with access to the drought data, the soil surveys, the vegetation maps, and a basic understanding of synoptic meteorology could have looked at April of 1935 and said, the probability of an extreme event this spring is higher than it has been in years. The conditions are assembled. The trigger is a matter of when, not whether. That person existed. Those data existed. The warning was not issued at the scale the risk required. And on April 14, 1935, the trigger arrived. The lesson of Black Sunday is not that extreme events are impossible to anticipate. It is that the anticipation requires saying clearly what the data already shows, before the event makes the point for you, in a way that cannot be ignored and cannot be undone. Part 19. The slow-motion dust bowl scenario. There is a version of this story that does not have a dramatic inflection point, no single Black Sunday, no one date on which historians will later say the Dust Bowl began, no iconic photograph of a wall of darkness advancing on a farmhouse, no moment of collective shock that forces a nation to confront what has been happening in plain sight. Instead, there is a sequence, a slow, grinding, almost imperceptible accumulation of conditions, losses and departures that adds up over years and then decades to something indistinguishable in its effects from what happened in the 1930s, but unfolding at a pace that never quite crosses the threshold of drama that would force a political response. This is the scenario that keeps agricultural scientists and soil conservationists up at night far more than the Black Sunday scenario does. And I want to describe it carefully because its very gradualism is not a reassuring feature. It is the most dangerous thing about it. Consider how this trajectory looks from inside it, year by year. In 2026, the dust events are severe. AQI 1400, Haboob warnings, satellite visible plumes, multi-vehicle crashes in near-zero visibility. Bad. Alarming to those paying attention, but not unprecedented in the sense that requires emergency declaration. The drought monitor shows the same red and brown colours it showed last year. Agricultural losses are high, but within the range that federal crop insurance was designed to handle. The news cycle moves on. In 2027, the agricultural losses are higher than 2026. Not dramatically higher, just incrementally worse. The CRP enrollment figures drop another few 100,000 acres. A few more miles of shelter belt come down somewhere in Kansas to make room for a wider equipment turning radius. The Ogallala water table in the Texas Panhandle drops another foot, or maybe 2 feet, quietly, underground, invisibly, registered only in the drilling logs of water, well contractors and the quarterly reports of groundwater conservation districts that almost nobody reads. Eastern Colorado, which degraded a full drought category in a single week in April 2026, does not recover. It holds at the new level, and then, in a bad month, drops further. None of these individually cross the threshold for emergency response. None of them generate a front-page story that stays on the front page. None of them produce the kind of visible, undeniable, photogenic disaster that moves federal bureaucracies from monitoring mode into action mode. Together, year by year, they represent a trajectory. And a trajectory, if you understand where it leads, is more important than any single data point along it. The question is whether anyone in a position to change the trajectory is watching it with sufficient attention to recognize what they are seeing before it becomes irreversible. The agricultural economics of this slow-motion scenario follow a pattern that has been documented in enough analogous historical cases that it is not speculative. It is a known sequence. When farming becomes progressively more marginal, when yields decline, input costs rise, water becomes more expensive to pump, and the land itself becomes less productive under sustained drought stress. The first response at the individual farm level is intensification. You plant more acres to compensate for declining yield per acre. You push the equipment harder and longer. You draw down financial reserves more aggressively to maintain cash flow. You take on debt against land values that haven't yet reflected the deteriorating conditions underneath them. You plant that marginal quarter section on the back of the property that you always knew was fragile, because you need the production and the crop insurance will cover you if it fails. This response is completely rational at the individual farm level. Any farm manager making decisions in real time with real financial obligations would likely make the same choices. But it is catastrophic at the system level, because intensification on degraded, drought-stressed soil does not stabilize the situation. It accelerates the degradation. The marginal quarter section that gets planted under drought conditions does not just fail to produce. It loses the residual vegetative cover that drought had weakened but not fully killed. It loses the soil structure that marginal cover had been maintaining. It becomes, after 1 or 2 failed seasons, more degraded than it was before you planted it. The farm that planted 1 extra marginal field to make up for declining core production will, within a few years, have 2 degraded fields instead of 1. The financial pressure to intensify is simultaneously the ecological pressure to accelerate the system's decline. The farm is doing the rational thing, the landscape is paying the price. The next stage in the sequence, when intensification fails to stabilize the economics, is abandonment. And here is where the modern slow-motion scenario diverges most visibly from the 1930s version, not in its outcome, but in its mechanism and its pace. In the 1930s, farm abandonment was dramatic. Families loaded what they could carry onto trucks and left. Photographs documented the exodus. The abandoned farmsteads, the empty towns, the stopped clocks and left-behind furniture became part of the visual record of the disaster. The abandonment was visible, sudden, and large enough in scale to be documented as a discrete historical event. In the modern slow-motion scenario, farm abandonment looks different. It looks like a bank in Amarillo quietly foreclosing on an underwater farm loan in the 4th quarter of 2028, after 3 consecutive crop insurance payouts have failed to keep the operation solvent because the insurance covered the crop loss, but not the cumulative soil degradation that is making each successive year's yields lower than the last. It looks like a 68-year-old farmer in Deaf Smith County whose children moved to Dallas and who has no buyer for the land at any price that makes sense, stopping production not with drama, but with exhaustion, just stopping, because there is no reason to continue and no energy left to find one. It looks like a 29-year-old who grew up on a High Plains farm, went to agricultural college, came back intending to take over the family operation, running the numbers for 2 years and deciding that the trajectory doesn't work, that the water is going, that the soil is going, that the economics are going, and making the rational individual choice to pursue a different career somewhere that isn't drying up. Fallow land in a drought is exposed land. The mechanism is different from the 1930s, but the physical outcome is identical. Large areas of unprotected, vegetatively denuded, loose surface soil sitting on a flat, dry, windy landscape with nothing to hold it down. The wind does not care whether the land became exposed because a family fled in a truck in 1936, or because a bank filed a foreclosure notice in 2028. It just finds the surface and begins its work. The population response follows the same pattern as the agricultural response, just stretched across a longer timeline and distributed across a larger geography in ways that make it harder to perceive as a unified phenomenon. The rural depopulation of the High Plains has already been ongoing for decades, driven by agricultural consolidation, mechanization, and the general economic migration towards cities that has characterized American demography since the mid-20th century. What the slow-motion Dust Bowl scenario does is accelerate that existing trend past the threshold where the communities left behind can maintain the infrastructure required to remain functional. Small towns across the Texas Panhandle, western Oklahoma, and southeastern Colorado have already lost their hospitals to consolidation, their schools to declining enrollment, their main street businesses to online retail and regional consolidation. What remains in many of these communities is a skeleton of essential services and a population that skews heavily elderly. The people who stayed because their roots were too deep to pull, or because they had nowhere else to go, or because they genuinely loved the land they were watching die. When the agricultural economics deteriorate past the point where even marginal farming is viable, those remaining residents lose the economic base that was sustaining even the skeleton. The grain elevator closes because there is no grain to move. The equipment dealer closes because there are no farmers buying equipment. The last doctor leaves because there are not enough patients to sustain a practice. The town does not disappear overnight. It just becomes, year by year, a little less capable of sustaining human life at the level of basic dignity. Measured across a decade timescale, this process constitutes the modern equivalent of the Great Migration, the displacement of a population from a region that can no longer support them, driven by the same combination of drought, soil failure, and economic collapse that drove the original Okies and Arkies down Route 66 toward California. It does not look like that migration. It does not produce the same photographs or the same songs or the same political shock. It produces instead a quiet demographic statistic in a Census Bureau report, a line in a county economic development study, a note in a regional Fed agricultural survey about declining farm loan performance. The catastrophe is the same. The visibility is not. This scenario does not require a Black Sunday. It does not require a single dramatic event to tip it into disaster. It requires only that the current trajectory continue for another 10 or 15 years without a meaningful course correction. And the current trajectory, as documented across every data set we have examined in this story, is pointing in exactly that direction without deviation. The soil is moving. The water is going. The farms are struggling. The towns are thinning. The protective infrastructure is declining. Each of these processes is individually gradual. Together they are a vector pointing toward an outcome that the 1930s generation would recognize immediately, even if it arrives without the black sky and the wall of dust that made their version impossible to ignore. The mystery, as I have said before and will keep saying until someone with the authority to act on it gives a different answer, is not what is happening. The mystery is why the response is so far behind the knowledge of what is coming. Part 20. The unanswered question. Let's come back to where we started. On March 15th, 2026, instruments in Lubbock, Texas recorded an air quality index of 1,400. Federal weather forecasters in Amarillo issued haboob warnings over agricultural land that is not a desert and was not supposed to become one. A multi-vehicle crash on a major highway occurred in near-zero visibility driven by blowing soil. NASA satellites captured dust plumes visible from orbit, originating from the same geographic source region as the storms of the 1930s. And somewhere in the middle of all of that, the federal government issued drought monitor updates, filed quarterly agricultural loss reports, and did not hold a single press conference using the words Dust Bowl. I want to take a moment and just lay out as plainly as I can everything we have established across this story, not as a summary, but as an inventory. Because sometimes the most important thing you can do with a complex body of evidence is stop and read it aloud in a single breath, so the cumulative weight of it becomes impossible to rationalize away piece by piece. In a NOAA database, the Oceanic Niño Index showed the specific ocean temperature configuration: cool tropical Pacific record warm North Atlantic, that Cook, Miller and Seeger identified in 2009 as the necessary first ingredient of the Dust Bowl recipe. Not similar to that configuration, not trending toward it, matching it. In the USDA's Conservation Reserve Program records, enrollment figures showed approximately 11 million fewer protected acres than the program's peak enrollment in 2007. 11 million acres of fragile, erosion-prone land that was under protective vegetative cover and is no longer. In the US Drought Monitor, 89% of Texas and 99% of Oklahoma were in some category of drought, with the current episode already exceeding in duration the early 1930s drought that preceded Black Sunday. We are past the historical comparison point. We are in territory the comparison was meant to warn us about. In the wildfire statistics, more than 1,100,000 acres had burned across the southern plains in the first quarter of 2026 alone, stripping protective cover from land that 6 years of drought had already weakened to the edge of failure. In the air quality records, a major American city registered an index value nearly 3 times the level the EPA classifies as hazardous, in a range the measurement scale was never designed to reach. In the operational vocabulary of federal weather forecasters, terminology borrowed from Saharan desert meteorology was appearing in routine plains forecast products. Every single one of these data points exists in a publicly accessible federal database or a published government report. None of them are hidden. None of them require special clearance or insider access to find. They are sitting there, openly, waiting to be assembled into the picture they collectively describe. And in the peer-reviewed scientific literature published 16 years ago, a model that has been tested, validated, and cited hundreds of times in subsequent research described the mechanism producing all of these conditions with precision. The recipe was written down, the ingredients were named, the feedback loops were quantified, the thresholds were identified. The researchers who wrote that paper did so explicitly because understanding the mechanism was the necessary first step toward preventing a recurrence. They handed us the answer to a question we hadn't finished asking yet. And then 16 years passed. We have the understanding, we have the data, we have the monitoring systems, satellite imagery updated daily, drought maps updated weekly, ocean temperature indices updated monthly, air quality measurements updated hourly. We have the policy tools. The Conservation Reserve Program exists. The shelter belt infrastructure, however reduced, exists and could be expanded. Conservation easement programs exist. The Natural Resources Conservation Service Technical Assistance Network exists. These are not theoretical constructs. They are operational federal programs with staff and budgets and established relationships with the farming communities they serve. They are funded at levels below what the current problem requires, and the funding trajectory has been declining rather than increasing, but the institutional architecture to scale them up exists. The scaffolding is there. What is missing is the decision to build on it. What we do not have, as of April 2026, is a federal agency or a senior official who is willing to stand in front of a camera and say the sentence that the data has been composing for 6 years. The same conditions that caused the Dust Bowl are present today. They were identified and described in peer-reviewed science 16 years ago, and the United States government needs to respond at a scale commensurate with what we know is happening to American soil. That sentence has not been said. I have looked for it. It is not there. And the absence of that sentence in the face of everything we have just inventoried is the most significant fact in this entire story. I want you to think about what the generation that lived through the 1930s would make of our current situation, because I find this comparison genuinely difficult to sit with, and I think you should too. The people who experienced the Dust Bowl did not have the Cook, Miller and Seeger paper. They did not have NOAA ocean temperature monitoring buoys feeding real-time data into publicly accessible indices. They did not have NASA Earth Observatory satellites capturing dust transport events from 200 miles above the atmosphere and posting the imagery online within 48 hours. They did not have a weekly National Drought Monitor map color-coded by severity. They did not have general circulation climate models capable of isolating the contribution of individual variables to large-scale atmospheric patterns. They had none of these things. They had people dying of dust pneumonia. They had children in rural Oklahoma hospitals with lungs full of silicate particles. They had farmers standing on their porches watching the topsoil of their entire operation blow east toward the Atlantic while they calculated whether they had enough money left to buy food for the next month. They had a sky that turned black at noon on a Sunday in April, and within months of that Sunday, they had created the Soil Conservation Service. They had funded and begun planting 220 million trees across the Great Plains. They had developed and begun deploying emergency conservation tillage practices on millions of acres. They had passed the legislation and allocated the resources for what became the conservation reserve concept. They moved. They moved fast. They moved at a scale commensurate with the problem, because the problem had made itself undeniable in the most visceral possible way, and the people in positions of authority in 1935 had the political courage to match the scale of their response to the scale of the crisis. We have everything they didn't have. We have the early warning system they were operating without. We have the mechanism decoded before the worst events rather than after. We have the variables tracked in real time rather than reconstructed from memory and mortality records. We have the historical comparison available not as living trauma, but as documented, analysed, modelled, peer-reviewed science. We have, in every technical and informational sense, a better position than they were in. And we have produced a smaller response. We have produced so far essentially no response at the scale the conditions warrant. We have produced monitoring and reporting and quarterly updates and declining program budgets. We have produced the documentation of a problem without the mobilization to address it. There is a word for the gap between what we know and what we do. In individual human psychology, we call it denial, though that word implies a kind of active resistance that may not fully capture what is happening in large institutional systems. In institutional systems, the gap has more prosaic names that are in some ways more troubling because they are more structural. Bureaucratic inertia, which means the tendency of large organizations to continue doing what they have been doing, because changing direction requires energy that the organization's incentive structure doesn't reward. Misaligned incentives, which means a policy architecture that compensates farmers for losses rather than preventing them, that funds insurance payouts rather than conservation investment, that makes it economically rational to expose fragile land rather than protect it. Political risk aversion, which means the calculation by officials who understand the problem that saying the words "Dust Bowl" out loud carries political and economic costs that silence does not, at least until the silence becomes impossible to maintain. Fragmented accountability, which means a system where every agency sees its piece of the data clearly and no agency has an explicit mandate to assemble the pieces into a response commensurate with what the assembled picture shows. None of these explanations require bad actors. None of them require a conspiracy or a deliberate suppression of information. They are the normal operating characteristics of large government systems under conditions of diffuse, slow-moving system-level risk. They are the institutional equivalent of the human tendency to delay the doctor's appointment for a symptom that has been developing gradually rather than appearing suddenly. The symptom would trigger immediate action if it appeared overnight. Because it has been developing for years, there is always a reason to wait one more quarter, one more budget cycle, one more growing season before escalating the response. The conditions visible from orbit over the southern plains in the spring of 2026 are not ambiguous. I want to be clear about that, because ambiguity is sometimes offered as a reason for institutional hesitation, and it does not apply here. The science describing what the current conditions mean is not contested in any serious scientific forum. The peer-reviewed literature on the Dust Bowl mechanism is not a fringe hypothesis awaiting confirmation. It has been tested, replicated, extended and built upon for 16 years. The policy mechanisms available to address the problem are not experimental or unproven. They are the same mechanisms that were deployed after the original Dust Bowl and that demonstrably worked. The only thing that is genuinely unclear, the only element of this entire story that remains a true mystery, is not what is happening to the soil of the southern plains. That part is documented, measured, and understood. The mystery is what is happening to the response. The Dust Bowl killed at least 7,000 Americans through dust pneumonia, malnutrition, and the cascading health consequences of prolonged displacement and poverty. It displaced 2.5 million people in the largest internal migration in American history up to that point. It destroyed 100 million acres of farmland, much of which has never fully recovered its original productivity. And it did all of this despite the fact that the warning signs were visible for years before the worst of it arrived. Visible to soil scientists, to agricultural extension agents, to anyone who drove across the southern plains in 1933 or 1934 and looked at what was happening to the ground. The disaster was not invisible in advance, it was ignored in advance. And the people who ignored it did not do so out of malice. They did so because the system they were operating in was not structured to translate the warning into action before the event made the cost of inaction undeniable. We're in that position now with better information and fewer excuses. The question this story leaves us with does not have an answer yet. It is being written right now in real time by decisions being made and not made in Washington. By USDA budget negotiations that will determine whether CRP rental rates increase enough to re-enroll vulnerable acres or continue their decline. By Farm Bill deliberations that will determine whether crop insurance incentives are restructured toward conservation or left in their current form. By individual farmers across the Texas Panhandle and southwestern Oklahoma making planting decisions this spring on land that 6 years of drought have left desperately vulnerable. By weather systems moving across the Pacific and the Atlantic, assembling and reassembling the atmospheric configuration that a peer-reviewed paper described 16 years ago as the trigger for the thing we're trying not to say. The storm is not a metaphor. The recipe is not theoretical. The silence is not an accident. And somewhere under a sky that instruments can no longer fully measure, on soil that has been losing its structure and its moisture and its protective cover for 6 consecutive years, the southern plains is waiting to find out what kind of story this turns out to be. The kind where the warning was heeded, or the kind where it wasn't. The 1930s generation didn't get to choose which story they were in. We still do. But that window, like the topsoil itself, does not stay open indefinitely.